Tonight, we're going to take a journey through our solar system, but not by looking at beautiful images of distant worlds or talking about what scientists discovered there. We're going to talk about something that rarely gets discussed honestly. Time, the actual time it takes to reach each planet in our solar system. Because when you see spacecraft visiting Mars or Saturn in documentaries, they make it look quick. Launch, journey, then arrival, all clean and simple, but the reality is far more brutal than most people realize, and by the end of tonight, you'll realize that exploring our solar system operates on timescales that most people can't even comprehend. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Here's what most people think when they hear about a mission to Mars. They imagine a spacecraft launching from Earth, traveling through space for a while, and landing on the red planet. Maybe they think it takes a few weeks, maybe a couple months at most. That sounds reasonable, right? Mars doesn't look that far away in diagrams of the solar system. It's the next planet over after Earth, our neighbour. But here's the reality. The fastest trip to Mars ever made took about 6.5 months. That was Mariner 6 in '69, and it didn't even land. It just flew past modern Mars missions, the ones that actually need to slow down and enter orbit or land, take about 7 to 9 months. Every single time, 7 to 9 months of travelling through empty space to reach a planet that's right next door in cosmic terms. And that's under ideal conditions when Earth and Mars are positioned favourably relative to each other. But before we can understand why it takes so long to reach Mars, we need to understand something fundamental about how orbital mechanics works. Because this isn't like driving a car where you point in the direction you want to go and press the accelerator. Space travel is governed by gravity, momentum, and the precise dance of celestial bodies that have been orbiting the Sun for billions of years. When we launch a spacecraft from Earth, we're not starting from a standstill. Earth is already moving and we're on a planet that's travelling around the Sun at about 18 1/5 miles per second. That's 600 miles per hour. The spacecraft inherits this velocity the moment it launches. You can't just point a spacecraft at Mars and fly straight there, because Mars isn't sitting still either. It's orbiting the Sun at about 15 miles per second in a different orbital path than Earth. So you're trying to reach a moving target while you yourself are moving on a completely different track. It's like trying to throw a ball to someone on a different merry-go-round while you're both spinning. Engineers solve this problem using what's called a Hohmann transfer orbit. This is the most fuel-efficient way to travel between two planets. You launch your spacecraft so that it enters an elliptical orbit around the Sun. One end of the ellipse touches Earth's orbit where you launched from. The other end touches Mars's orbit where you want to arrive. The spacecraft coasts along this ellipse using almost no fuel during the journey until it meets Mars on the other side. But here's the critical part. For this to work, Mars needs to be in the right position when you arrive. Launch too early and your spacecraft will reach Mars's orbital path before Mars gets there. Launch too late and you'll arrive after Mars has already passed. The timing has to be essentially perfect. This creates what's called a launch window, a specific period of time usually lasting a few weeks when the planets are aligned correctly for a mission to work for Mars. These launch windows open approximately every 26 months. That's how long it takes for Earth and Mars to return to the same relative positions in their orbits. If you miss your launch window, you don't just wait a few weeks, or you wait 2 years until the planets align again and another opportunity opens. This is why you see Mars missions clustered together. In 2020, 3 separate missions launched to Mars. NASA's Perseverance rover, China's Tianwen-1 orbiter and rover, and the United Arab Emirates Hope orbiter. They all launched within a few weeks of each other because they were all targeting the same launch window. The next window didn't open until 22. The one after that opened in 24. This waiting game adds enormous complexity to space exploration. It means mission planning has to happen years in advance. If you discover a problem with your spacecraft a month before the launch window, you can't just say, "We'll launch next month." You have two choices: fix it in time and launch, or wait 2 years. The pressure is immense. Missions that cost billions of dollars and decades of work can come down to meeting a launch deadline that won't come around again for years. Now, let's talk about what happens during those 7 to 9 months traveling to Mars. The spacecraft isn't constantly firing its engines. That would require impossible amounts of fuel. Instead, it's coasting. The rocket burns hard during launch to escape Earth's gravity and place the spacecraft on the correct trajectory. Maybe there are a few small correction burns along the way to adjust the path. But mostly, the spacecraft is just falling through space following the curved path of its transfer orbit. For the people controlling the mission, these months are nerve-wracking. You can't call the spacecraft back if something goes wrong. You can't send a repair crew. If a critical system fails, the mission is over. You've spent years building the spacecraft, hundreds of millions or billions of dollars launching it, and months watching it travel through the void, and all of that can be lost in an instant if something breaks. The communications delay adds to the tension. Radio signals travel at the speed of light, but even light takes time to cross the distance between Earth and a spacecraft approaching Mars. When the spacecraft is near Mars, signals take about 12 to 14 minutes to travel each way, depending on where the planets are in their orbits. That means there's a 24 to 28-minute round-trip communication time. If mission control sees a problem and sends a command to fix it, 24 minutes pass before they know whether the fix worked. If the spacecraft encounters a problem that needs immediate attention, it has to handle it autonomously. By the time Earth knows there's a problem and responds, it could be too late. This is exactly what happened with many early Mars missions. The Soviet Union tried to reach Mars multiple times in the 1960s and early 70s. Most of their missions failed. Mars 2 and Mars 3 both reached Mars orbit in 1971, but their landers failed shortly after touchdown. Mars 6's lander failed seconds before reaching the surface in 1973. Mars 7 missed the planet entirely due to a navigation error. NASA had better luck, but even they lost missions. Mars Observer, launched in 1992, lost contact just before entering Mars orbit. 11 months of travel, hundreds of millions of dollars, gone in an instant. Mars Climate Orbiter, in 1998, crashed into Mars because one team was using metric units and another was using imperial units. A simple conversion error destroyed the entire mission. Mars Polar Lander in 1999 crashed because of a software error that shut off its engines too early. These weren't failures of technology or engineering skill. They were failures that happened because space travel is unforgiving. One small error, one component failure, one miscalculation, and months or years of work vanish, and you don't get a second chance until the next launch window opens. But Mars is easy compared to the outer planets. Mars is our neighbour, relatively close, relatively quick to reach. When you start talking about Jupiter, Saturn, Uranus, and Neptune, the travel times expand to timescales that challenge human patience and institutional commitment. Let's talk about Jupiter. Jupiter is the giant of our solar system, more massive than all the other planets combined. It orbits the Sun at an average distance of about 483 million miles or 77 million kilometers. Earth orbits at about 93 million miles, so Jupiter is roughly 5 times farther from the Sun than we are. The first spacecraft to reach Jupiter was Pioneer 10, launched in March 1972. It took 21 months to get there, nearly 2 years of travel to reach Jupiter. Pioneer 11, launched in April 1973, took about 20 months. The Voyager missions, launched in 1977, had better trajectories. Voyager 1 took about 18 months to reach Jupiter. Voyager 2 took about 22 months. but flew a different route that also took it past Saturn, Uranus and Neptune. The Galileo spacecraft, launched in October 1989, took 6 years to reach Jupiter, not because the spacecraft was slow, but because it took a complicated route, flying past Venus once and Earth twice to use gravitational assists to gain speed. The direct path would have required more fuel than the rocket could carry, so instead, Galileo took the long way, swooping through the inner solar system multiple times, using planetary flybys to gradually build up enough velocity to reach Jupiter. Juno, launched in August 2011, took 5 years to reach Jupiter, also using gravity assists from Earth. Cassini, which was heading to Saturn, flew past Jupiter in late 2000 after about 4 years of travel, using Jupiter's gravity to help slingshot itself towards Saturn. The fastest trip to Jupiter was New Horizons, launched in January 2006. It reached Jupiter in just 13 months. New Horizons held the record for the fastest spacecraft ever launched. It left Earth at about 36,000 km relative to the Sun. Even at that incredible speed, it still took over a year to reach Jupiter. And New Horizons didn't slow down at Jupiter. It flew straight past at high speed, using Jupiter's gravity to boost itself even faster towards Pluto. If it had needed to slow down and enter orbit around Jupiter, the trip would have taken much longer because slowing down requires fuel and time. Think about what this means for mission planning. If you're designing a mission to orbit Jupiter, you're committing to at least 5 years of travel time. Years where your spacecraft is in transit, where you can't fix problems, where you can only monitor and hope everything keeps working. And that's assuming you launch during a good window and use gravitational assists to minimize travel time. A direct Hohmann transfer to Jupiter would take longer. The spacecraft would need to launch when Earth and Jupiter are positioned correctly, travel along an elliptical orbit for roughly 2.5 to 3 years, then fire its engines to slow down and enter Jupiter orbit. But using gravitational assists is more efficient. You launch towards Venus or back toward Earth. Use those planets' gravity to bend your trajectory and increase your speed, then head outward toward Jupiter with more velocity than you started with. It takes longer in terms of total time, but it requires less fuel, which means you can carry more scientific instruments or a bigger antenna for communications. Every kilogram matters when you're launching a spacecraft into deep space. Fuel is heavy. The more fuel you need, the bigger your rocket has to be, and the more expensive music the launch becomes. So, mission planners constantly balance travel time against fuel requirements. Faster trips require more fuel. Fuel requires bigger rockets. Bigger rockets cost more money. At some point, the cost becomes prohibitive, and you accept the longer travel time to make the mission affordable. Saturn is even farther. Saturn orbits at an average distance of about 86 million miles from the Sun, or 1.4226 billion kilometers, nearly 10 times farther than Earth. The first spacecraft to reach Saturn was Pioneer 11 in September 1979. It had launched in April 1973. That's 6.5 years of travel. 6.5 years. Think about what that means. The scientists and engineers who built Pioneer 11 in the early 1970s waited over 6 years to see their spacecraft reach its destination. Some of them had moved on to other projects. Some had retired. The graduate students who worked on the mission in 1973 were well into their careers by the time it arrived at Saturn. Voyager 1 reached Saturn in November 1980, 3 years after launch. But Voyager 1 had help. It flew past Jupiter first, using Jupiter's enormous gravity to accelerate and change course towards Saturn. Without that assist, the trip would have taken much longer. Voyager 2 reached Saturn in August 1981, 4 years after launch. Having also used a Jupiter assist, the Cassini mission, launched in October 1997, took nearly 7 years to reach Saturn, arriving in July 2004. 7 years. 7 years of coasting through space, past the orbit of Mars, through the asteroid belt, past Jupiter, out to the ring giant. During those 7 years, entire careers progressed. People got married, had children, watched those children grow from infants to elementary school students, and the whole time, Cassini was out there in the dark, travelling alone, following its predetermined path, completely beyond human help if anything went wrong. The engineers who designed Cassini systems had to think about reliability on timescales that exceed most product lifetimes. Your car might need to work reliably for 10 or 15 years. Cassini needed to work reliably for 7 years just to reach Saturn, then continue working in orbit around Saturn for years afterward. In the end, Cassini operated for 20 years total, 13 of those years at Saturn, making it one of the most successful planetary missions ever. But that success required planning, redundancy, and careful engineering that anticipated problems years before they might occur. Every system had backups. Every component was tested, music, and retested. Every line of software was checked and verified, because once Cassini launched, there was no going back, no repairs, no second chances. Uranus and Neptune are even more extreme. These ice giants orbit in the cold outer reaches of the solar system, so far from the sun that they receive almost no warmth or light. Uranus orbits at about 1,074,000,000 miles from the sun, or 2.871 billion kilometers. Neptune orbits at about 2,794,000,000 miles, or 4.497 billion kilometers. These are distances so vast that even light from the sun takes hours to reach them. Sunlight takes about 8 minutes to reach Earth. It takes about 2 hours and 40 minutes to reach Uranus. It takes about 4 hours to reach Neptune. When you're that far from the sun, solar panels don't work well because there's not enough sunlight to generate power. Spacecraft heading to the outer solar system use radioisotope thermoelectric generators instead. These are essentially nuclear batteries that convert the heat from radioactive decay into electricity. They can run for decades without needing any external energy source. But they're expensive, complex, and politically sensitive because they contain plutonium. Only one spacecraft has ever visited Uranus and Neptune. Voyager 2 launched in August 1977, taking advantage of a rare planetary alignment that happens only once every 75 years. This alignment allowed Voyager 2 to visit Jupiter, Saturn, Uranus, and Neptune in sequence, using each planet's gravity to accelerate toward the next. Without this alignment, visiting all 4 planets would have required multiple separate missions, each taking decades. Voyager 2 reached Jupiter in July 1979. After about 23 months of travel, it reached Saturn in August 1981 after 4 years total. It reached Uranus in January 1986 after 8.5 years. It reached Neptune in August 1989 after 12 years. 12 years from launch to Neptune. 12 years. The people who built Voyager 2 music in the mid-1970s were in a completely different phase of their lives when it finally reached Neptune. Young engineers in their 20s, music, were in their late 30s. Mid-career scientists were nearing retirement. The technology landscape had completely changed. When Voyager 2 launched, personal computers barely existed. The spacecraft's computer had 8 kilobytes of memory. 8 kilobytes. Your phone has millions of times more memory than that. But that tiny computer had to be reliable enough to run for 12 years without any hardware repairs. And it worked. The cameras functioned. The instruments collected data. The antenna pointed back toward Earth. The nuclear battery provided power. Everything worked, even after more than a decade in the hostile environment of deep space. There's something profound about missions like Voyager 2. They require a kind of patience that's almost alien to modern society. We're used to instant results. We send a message and expect a reply in seconds. We order something online and expect delivery in days. We start a project and want to see results within weeks or months. But planetary missions operate on completely different timescales. You design a spacecraft that won't reach its destination for a decade. You build systems that need to function reliably for years beyond that. You commit to a project knowing you might retire before it's finished. You accept that the data you're hoping to collect won't arrive until you're a different person living in a different world. This is why space exploration requires institutional commitment, not just individual passion. A single person can't sustain a 12-year mission alone. You need organizations that persist across time, that maintain knowledge and expertise as people come and go, that can hand off responsibility from one generation of scientists and engineers to the next. NASA's Jet Propulsion Laboratory has been operating planetary missions continuously since the 60s. People retire, new people are hired, technology changes, budgets fluctuate, but the missions continue. Voyager 1 and Voyager 2 are still operating today, nearly 50 years after launch. They're now in interstellar space, beyond the influence of the sun's solar wind, sending back data about a region of space music no human-made object has ever visited. They're so far away that radio signals take over 22 hours to reach Voyager 1 and over 18 hours to reach Voyager 2. The people operating these spacecraft now weren't even born when the Voyagers launched. They are maintaining and commanding machines built before they existed, using technology from the 1970s, communicating across billions of miles of empty space. Now, let's talk about the inner planets. Mercury and Venus, these are closer to the Sun than Earth, so you might think they'd be easier to reach. They're not. The problem is energy. When you're traveling outward in the solar system toward Mars, Jupiter, or Saturn, you're climbing up out of the Sun's gravity well. Your spacecraft starts with Earth's orbital velocity, then uses its rockets to add more speed and move to a higher, slower orbit. When you're traveling inward toward Mercury or Venus, you're falling down into the Sun's gravity well. You need to slow down, reduce your orbital velocity, and drop into a lower, faster orbit. Slowing down in space is just as hard as speeding up. It requires fuel, and the closer you want to get to the Sun, the more you need to slow down and the more fuel you need. This makes Mercury particularly difficult to reach. Mercury orbits very close to the Sun at an average distance of about 36 million miles. To reach Mercury, a spacecraft needs to lose most of Earth's orbital velocity. Earth travels around the Sun at about 18 1/2 miles per second. Mercury travels at about 29 1/2 miles per second because it's deeper in the Sun's gravity well. But to drop down to Mercury's orbit, you first need to slow way down from Earth's speed. Let yourself fall toward the Sun, then speed back up as you approach Mercury. The energy requirements are enormous. The first spacecraft to visit Mercury was Mariner 10, launched in November 1973. It used a Venus gravity assist to bend its trajectory and reduce the fuel needed. Even with this assist, it took about 5 months to reach its first Mercury flyby in March 1974. But Mariner 10 didn't orbit Mercury. It flew past 3 times using a trajectory that brought it back to Mercury every 6 months. The Messenger spacecraft launched in August 2004 took 6 1/2 years to enter Mercury orbit, 6 1/2 years to reach a planet that's closer to the Sun than we are. Why so long? Because Messenger couldn't carry enough fuel for a direct trip. Instead, it flew a complicated trajectory that included 1 Earth flyby, 2 Venus flybys, and 3 Mercury flybys before finally slowing down enough to enter orbit in March 2011. Each flyby used the planet's gravity to adjust Messenger's speed and trajectory, gradually bringing it into the right position and velocity to orbit Mercury. The spacecraft flew billions of miles through the inner solar system, looping past Earth, Venus, and Mercury multiple times over 6 1/2 years, all to reach a planet that's only about 48 million miles from Earth at its closest. A joint European and Japanese mission launched in October 2018 is taking an even longer route. It won't enter Mercury orbit until late 25. 7 years of travel. The spacecraft will perform 9 planetary flybys total. 1 Earth flyby, 2 Venus flybys, and 6 Mercury flybys. Each one adjusting its trajectory a little more, slowing it down a little more, until it finally has the right velocity to orbit Mercury. This is the reality of travelling to the inner solar system. You can't just point your spacecraft toward the sun and fire your engines. The energy requirements are too high. Instead, you have to dance through the inner planets, using their gravity to gradually change your path and speed over years of careful maneuvering. Venus is somewhat easier to reach than Mercury because it's not as deep in the Sun's gravity well. Venus orbits at about 7 million miles from the Sun, between Earth's orbit at 93 million miles and Mercury's orbit at 36 million miles. The Mariner 2 spacecraft, launched in August 1962, took about 3.5 months to fly past Venus. That was humanity's first successful visit to another planet. 3.5 months to reach our nearest planetary neighbour. Later, missions to Venus had varying travel times depending on their trajectories and objectives. The Soviet Venera landers took about 4 to 5 months to reach Venus. Magellan, launched in May 1989, took 15 months to reach Venus using multiple orbits around the Sun to position itself correctly. The Parker Solar Probe, currently studying the Sun, uses Venus gravity assists as part and music of its mission. Each Venus flyby bends Parker's trajectory music closer to the Sun. The probe flies past Venus every few months as part of its complex orbital pattern. Music gradually spiraling inward to get closer and closer to the Sun. These repeated Venus encounters are planned years in advance, each one precisely timed to adjust Parker's orbit by the exact amount needed for its scientific mission. Now, let's talk about what these travel times mean for human exploration. Every mission we've discussed so far has been robotic. Spacecraft carrying cameras, sensors, and scientific instruments, but no people. Robots can wait years in hibernation. They don't need food, water, or air. They don't get bored, lonely, or stressed. They don't age. A robot can travel for a decade and arrive in perfect condition, ready to work. Humans can't. Humans need life support systems. Air to breathe, water to drink, food to eat, waste disposal, temperature control, radiation shielding. All of that. Music adds mass. Mass requires more fuel to accelerate and decelerate. More fuel requires bigger rockets. Bigger rockets cost more money, but the real problem is time. 7 to 9 months to Mars might be acceptable for a human crew. Difficult, but possible. The journey would be longer than any current space station mission, but not impossibly longer. Astronauts have spent over a year on the International Space Station. The physical challenges of a Mars journey would be severe. Radiation exposure from cosmic rays and solar particle events, bone and muscle loss from extended weightlessness, psychological stress from confinement in a small spacecraft. But these problems have potential solutions. Radiation shielding, exercise regimens, psychological support. A Mars mission is technically possible with current or near-future technology. But Jupiter, 5 to 6 years minimum travel time, that's 5 to 6 years in a small spacecraft. No resupply, no medical evacuation, no possibility of turning back if something goes wrong. Every piece of food, every drop of water, every breath of air has to be carried from Earth or recycled with perfect efficiency. Any equipment failure could be catastrophic. A leak in the life support system, a malfunction in the water recycler, a failure of the radiation shielding. Any of these could be deadly, and help is months or years away. The psychological toll would be immense. 6 years in a confined space with the same small group of people, no privacy, no escape, no connection to Earth except for delayed radio messages. The communication delay to Jupiter varies from about 35 to 50 minutes one way depending on the planet's positions. That means a 70 to 100-minute round-trip time for any conversation. You could ask Mission Control a question and wait over an hour and a half for a response. If you had an emergency, if someone got sick or injured, if a critical system failed, you couldn't have a real-time conversation. With Earth, to figure out what to do, you would send a message describing the problem, then wait over an hour for Earth's response, then implement whatever solution they suggested, then wait another hour to tell them if it worked. In that time, a sick person could deteriorate. A failing system could cascade into multiple failures. A small problem could become a catastrophe. The crew would need to be almost completely autonomous, capable of handling any conceivable emergency without help from Earth. And that's just the journey to Jupiter. You'd then need to do science at Jupiter, which could take months or years, then travel back, total mission time, over a decade, away from Earth, away from family, away from everything familiar. By the time you returned, the world would have moved on. Your children would be grown. Your friends would have lived years of life without you. Technology would have advanced. Politics would have changed. You'd be returning to a world that wasn't quite the same one you left. Saturn would be even worse. 7 years to get there. Time at Saturn for exploration and science. 7 years to return. 15 to 20 years total. Neptune. 12 years one way, 25 years for a round trip. You could launch in your 20s and return in your late 40s. A quarter century of your life spent on a single mission. Your entire career. A significant fraction of your entire life. These timescales exceed anything humans have ever attempted. The longest any human has spent in space continuously is 437 days. That's about 14 and 1/2 months. Russian cosmonaut Valery Polyakov set that record on the Mir space station from January 1994 to March 1995. He experienced all the health problems associated with long-duration spaceflight: bone density loss, muscle atrophy, cardiovascular deconditioning, vision problems from fluid shifts in his skull. But he survived and eventually recovered after returning to Earth. Now imagine 25 years in space, 12 years of radiation exposure, 12 years of bone loss, 25 years of muscle atrophy. Could a human body even survive that? We don't know. We've never tried. We don't know if the human body can handle decades in space. We don't know if bones would become so brittle that they'd break under the slightest stress. We don't know if muscles would deteriorate to the point where astronauts couldn't function. We don't know if the accumulated radiation dose would cause cancer or other health problems. We don't know if the psychological stress would break people's minds. There are too many unknowns, too many risks, and all of that assumes the spacecraft works perfectly for decades. No major malfunctions, no critical failures, nothing that would jeopardize the mission. The engineering challenges are staggering. Every system would need to function reliably for 20 or 30 years. Pumps, valves, computers, life support systems, propulsion, navigation, communication, everything. One major failure could doom the entire crew. This is why human exploration of the outer solar system remains science fiction. Not because we lack the rocket technology. We could probably build rockets powerful enough to send humans to Jupiter or Saturn, but because we can't yet solve the human factors problems, the biology, the psychology, the life support, the reliability, the time, we can't yet commit human beings to missions lasting decades. So, instead, we send robots, patient, tireless robots that can wait years to reach their destinations, then work for years or decades sending data back to Earth. Voyager, Cassini, Galileo, Juno, New Horizons. These missions have given us incredible knowledge about the outer solar system, but they required patience, institutional patience spanning decades, political patience to keep funding missions that wouldn't produce results for years, personal patience from the scientists and engineers who dedicated large portions of their careers, music, to single missions. The Cassini mission exemplifies this. Planning began in the 1980s. The spacecraft was built in the 1990s. It launched in 1997. It arrived at Saturn in 2004. It explored Saturn and its moons until 2017, when it was deliberately crashed into Saturn's atmosphere to avoid contaminating potentially habitable moons. From initial planning to end of mission, Cassini spanned more than 30 years. People spent entire careers on Cassini. Graduate students who joined the mission in the 1980s were retiring scientists when the mission ended, principal investigators who started the project in their 30s, finished it in their 60s. Cassini became a thread connecting generations of planetary scientists. Early career researchers cut their teeth on Cassini data. Senior scientists ended their careers analyzing the mission's final observations. The knowledge gained was immense. Cassini discovered lakes of liquid methane on Titan. It found geysers of water erupting from Enceladus, suggesting a subsurface ocean. It observed Saturn's rings in unprecedented detail. It watched storms rage across Saturn's atmosphere. It provided decades worth of data that scientists are still analyzing today. But it required 30 years of commitment, 30 years of funding, support and dedication from institutions and individuals who believed the science was worth the wait. There's a lesson here about what space exploration really costs. It's not just money, although money is certainly part of it. It's time. Time measured not in months, but in years and decades. Time that exceeds human attention spans, political cycles and funding timelines. We live in an era of immediate gratification. We expect results now. We want to see progress quickly. But the solar system doesn't care about our impatience. The distances are what they are. The laws of physics are what they are. You can't travel from Earth to Neptune faster than the laws of orbital mechanics allow. No matter how much you want to, you can't bypass the years of travel time. You can't skip ahead to the exciting part where the spacecraft arrives and starts sending back pictures. You have to wait. And waiting is hard. It's hard for individuals who want to see results in their lifetimes. It's hard for politicians who want achievements they can point to before the next election. It's hard for funding agencies that want to show progress to justify continued investment. But it's necessary if we want to explore the solar system. If we want to understand these distant worlds, we have to accept the time it takes. We have to commit to missions that won't produce results for 5, 10, 15 years. We have to support scientists and engineers who dedicate their careers to single missions. We have to maintain institutions that can persist across decades. This is what makes robotic space exploration so remarkable. Not just the technology, although the technology is impressive, not just the science, although the science is incredible, but the patience, the willingness to wait years or decades for knowledge, the commitment to projects that exceed individual careers, the faith that the discoveries waiting. At the end of these journeys will be worth the time invested. Every planet we've visited, every moon we've photographed, every piece of data we've collected from the outer solar system represents this patience. Voyager's images of Neptune came after 12 years of travel. Cassini's discoveries at Saturn came after 7 years of travel and 13 more years in orbit. New Horizons, images of Pluto came after 9 1/5 years of travel through the outer solar system. These weren't quick projects. They were epic journeys spanning significant fractions of human lifetimes, and they're not over. Voyager is still operating, still sending data from interstellar space. New Horizons is still flying deeper into the Kuiper Belt, still making observations. The data from these missions will be analysed for decades to come. Papers will be published based on Cassini observations for years. New insights will emerge as scientists develop new techniques for analysing old data. These missions echo through time, their influence extending far beyond their operational lifetimes. Let's also talk about the missions that didn't work. Because for every successful mission that reached its destination, music, and produced incredible science, there were failed missions that didn't. The Soviet Union's early attempts to reach Mars mostly failed. More than a dozen missions launched toward Mars in the 1960s and early 70s. Most of them failed before arrival, during arrival or shortly after landing. Years of work, months of travel, billions of rubles spent, all resulting in silence. NASA has had failures too. Mars Climate Orbiter crashed into Mars in 1999 after 9 months of travel. Mars Polar Lander crashed in 1999 after 11 months of travel. The Japanese Nozomi spacecraft launched toward Mars in 1998, failed to enter orbit after 5 years of travel. These failures are heartbreaking for the people involved. Imagine working for years to design, build, and test a spacecraft, watching it launch successfully, monitoring it for the months as it travels. Through space, everything working perfectly. Then something goes wrong in the final moments. A software error, a mechanical failure, a navigation mistake. Suddenly years of effort vanish. The spacecraft is gone. The mission is over. All that time, all that work, all that anticipation, all lost. But failures are part of exploration. They always have been. Early explorers of Earth's oceans lost ships. Early aviators crashed planes. Early attempts to climb mountains ended in tragedy. Exploration music is risky. It involves going to places we've never been, trying things we've never tried, pushing the boundaries of what's possible. Sometimes it works and sometimes it doesn't. The key is learning from failures. Mars Climate Orbiter crashed because of a unit conversion error. Now, every mission includes extensive checks to prevent similar mistakes. Mars Polar Lander crashed because of a software error in its landing sequence. Now, landing software is tested and validated much more thoroughly. Each failure teaches lessons that make future missions more likely to succeed. But the time cost of failure is brutal. If a Mars mission fails, you've lost not just the spacecraft and the money, but also 7 to 9 months of travel time. If you want to try again, you have to wait for the next launch window in 26 months, then build a new spacecraft, then wait 7 to 9 more months for it to reach Mars. From failure to successful retry could easily be 5 years, 5 years of additional waiting on top of all the time already invested. For outer planet missions, the time cost is even worse. If a Jupiter mission fails, you've lost 5 to 6 years of travel time. Building and launching a replacement could take years. You might be looking at a decade or more before you get another chance. This is why mission planning is so careful, why testing is so thorough, why every component is checked and rechecked. Because failure means years of lost time, and in space exploration, time is the most valuable resource. You can sometimes get more funding, you can build new spacecraft, but you can't get back the years lost to a failed mission. So, let's put this all together. Here's what we've learned tonight. Mercury takes about 5 months minimum for a flyby, or 6 to 7 years to orbit using gravity assists. Venus takes about 3.5 to 4 months for a flyby, or up to 15 months for an orbiter. Mars takes about 7 to 9 months under ideal conditions, with launch windows opening every 26 months. Jupiter takes about 13 months minimum for a fast flyby like New Horizons, or 5 to 6 years for an orbiter. Saturn takes about 6 to 7 years to reach an orbit. Uranus takes about 8.5 years if you use a Jupiter gravity assist like Voyager 2 did. Neptune takes about 12 years using multiple gravity assists. These aren't just numbers, they're timescales that challenge human nature. They're commitments that exceed election cycles, funding periods, and often individual careers. They require patience that's almost superhuman. Faith that the discoveries waiting at journey's end will be worth the years spent getting there. And yet, we've done it. We've sent spacecraft to every planet in the solar system. We've orbited some of them for years, studying them in detail. We've landed on Mars multiple times. We've sent probes diving into Jupiter's atmosphere. We've put a spacecraft in orbit around Saturn for 13 years. We've flown past the ice giants of the outer solar system. We've even sent spacecraft beyond the solar system entirely into interstellar space. All of this required patience. Patience from the scientists who proposed these missions. Patience from the engineers who built the spacecraft. Patience from the funding agencies that supported them. Patience from the public that paid for them. And patience from the people operating the missions, watching data slowly arrive from billions of miles away year after year. This is the reality of exploring our solar system. It's not quick. It's not easy. It's not something you can do on a whim. It requires commitment measured in decades. Technology that must function reliably for years. Support that persists through changes in politics, budgets, and public interest, but the rewards are extraordinary. Every image of a distant world, every measurement of an alien atmosphere, every discovery of an unexpected moon or ring or ocean, every piece of knowledge about how planets form, how they evolve, what they're made of. All of it comes from our willingness to wait, our patience to let spacecraft travel for years through the void, our commitment to missions that won't produce results until long after they launch. When you see a stunning image of Saturn's rings or a panorama of Mars's surface, remember that image represents years of travel time, years of waiting, years of hope that the spacecraft would survive the journey and the cameras would still work when it arrived. That's what makes these images precious, not just their beauty, but the patience required to obtain them. The next time you hear about a new planetary mission launching, remember what you learned tonight, that spacecraft has a long journey ahead, months or years of travel through empty space. The people who built it will wait anxiously for it to arrive. Some of them will retire before the mission ends. Some of them will spend the prime years of their careers operating it. All of them will invest a significant portion of their lives into this single mission. And if everything works, if the spacecraft survives the journey and the instruments function and the communication systems hold up, we'll gain new knowledge about worlds we can only dream of visiting. We'll see places no human has ever seen up close. We'll discover things we never imagined, all because some people were patient enough to wait. Thank you for joining me on this journey through time and space. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me continue making these deep dives into the cosmos. And remember, when you look up at the planets in the night sky, those aren't just distant lights. They're destinations that require years of patience to reach. But that patience has given us some of humanity's greatest achievements. The exploration of our solar system, one patient mission at a time. Now, let's dig deeper into some specific missions because understanding the details makes the achievements even more remarkable. Take the Perseverance rover. Currently exploring Mars, Perseverance launched on July 30th, 2020 aboard an Atlas V rocket from Cape Canaveral. The spacecraft travelled approximately 23 million miles through space, not in a straight line, but following a curved trajectory that intersected with Mars's orbit at exactly the right moment. The journey took 6 months, 22 days, and about 18 hours. During that time, mission controllers could only watch and wait. They sent occasional commands to check systems and make small trajectory corrections. But mostly, the spacecraft was on its own. cruising through the void at thousands of miles per hour. On February 18th, 2021, Perseverance reached Mars. The entry, descent, and landing sequence, often called the 7 minutes of terror, was completely autonomous. The spacecraft entered the Martian atmosphere at about 12,000 miles per hour, a speed so fast that the friction with the thin atmosphere heated the heat shields to about 2400 F or 1366 UC. That's hot enough to melt steel. The heat shield protected the spacecraft, but it couldn't communicate during this phase. The plasma surrounding the spacecraft blocked radio signals. Mission Control on Earth had no idea if Perseverance was surviving the entry. They could only wait. The spacecraft deployed a parachute to slow down further. Then it dropped the heat shield. Radar measured the distance to the ground. The parachute detached and retro rockets fired, slowing the descent even more. Finally, the sky crane lowered the rover on cables to the surface while the descent stage hovered above. Once the rover touched down, the cables cut and the descent stage flew away to crash at a safe distance. All of this happened in 7 minutes. 7 minutes of precisely choreographed events. Any failure at any step and music would have destroyed the mission, and Mission Control couldn't help. Radio signals from Mars take anywhere from 5 to 20 minutes to reach Earth, depending on where the planets are in their orbits. During Perseverance's landing, the delay was about 11 minutes. By the time Mission Control saw the spacecraft enter the atmosphere, it had already been on the surface for 4 minutes. Successful or crashed, they watched the landing like a recording of events that had already happened. Every mission to Mars experiences this same stress. 7 months of travel followed by 7 minutes where everything can go wrong and you can't do anything about it. And Mars is relatively easy compared to the outer planets. Consider the Galileo mission to Jupiter. Galileo launched in October 1989 aboard the Space Shuttle Atlantis. The original plan was to use a powerful Centaur upper stage to send Galileo directly to Jupiter. But after the Challenger disaster in 1986, NASA banned Centaur stages from shuttle flights because they were considered too dangerous. So mission planners had to redesign Galileo's trajectory. Instead of going directly to Jupiter, Galileo flew a circuitous route through the inner solar system. It flew past Venus once in February 1990, using Venus's gravity to change course. Then it flew past Earth twice, once in December 1990 and again in December 1992. Each Earth flyby added music velocity, accelerating Galileo toward the outer solar system. Between the 2 Earth flybys, Galileo became the first spacecraft to visit an asteroid, flying past Gaspra in October 1991. After the second Earth flyby, Galileo flew past another asteroid, Ida, in August 1993. During this flyby, Galileo discovered that Ida had its own tiny moon. Later named Dactyl, this was the first confirmed discovery of a moon orbiting an asteroid. Finally, in December 1995, 6 years after launch, Galileo reached Jupiter, but the mission had problems. The main antenna, a large umbrella-like structure that was supposed to unfold after launch, failed to open completely. Several of the ribs were stuck. Engineers tried everything they could think of to free the antenna. They commanded it to open and close repeatedly. They rotated the spacecraft, hoping centrifugal force would help. They heated and cooled the mechanism, trying to expand and contract the stuck parts. Nothing worked. The main antenna, which was supposed to transmit data at 134,000 bits per second, was useless. Galileo had to rely on its much smaller low-gain antenna, which could only transmit at 10 bits per second. 10 bits per second. That's more than 13,000 times slower than planned. To put that in perspective, a typical smartphone loads data at millions of bits per second. Galileo had to transmit Jupiter images and scientific data at 10 bits per second. The mission wasn't cancelled, though engineers worked around the problem. They upgraded the receiving antennas on Earth to pick up weaker signals. They developed better data compression algorithms to squeeze more information into less data. They prioritized the most important observations, and Galileo succeeded. Despite the antenna problem, despite the 6-year journey, despite all the challenges, Galileo spent 8 years orbiting Jupiter, making 34 orbits. Flying past Jupiter's major moons multiple times each, it discovered evidence of subsurface oceans on Europa, Ganymede, and Callisto. It observed volcanic activity on Io, Jupiter's innermost large moon, watching as eruptions changed the surface. It measured Jupiter's intense magnetic field. It studied the planet's atmospheric dynamics. It released a probe into Jupiter's atmosphere that sent back data during its descent before being crushed by the pressure. The mission finally ended in September 2003 when Galileo was deliberately crashed into Jupiter's atmosphere. This was done to prevent the spacecraft from eventually crashing into Europa and potentially contaminating its subsurface ocean with Earth microbes. Even at the end of its life, even as it plunged to destruction, Galileo was still transmitting data. The mission spanned 14 years from launch to end. 14 years. The engineers who designed Galileo in the early 80s were retiring when it was destroyed. The spacecraft had outlasted some of the people who built it. It had provided data that kept planetary scientists busy for years during its operation and continues to be analysed today. This is what deep space exploration looks like up close. Years of travel, years of operation, decades of total mission lifetime, problems that arise and have to be solved creatively, successes that come from persistence and ingenuity. Let's talk about New Horizons and the journey to Pluto. New Horizons launched in January 2006. At the time, Pluto was still classified as the 9th planet. By the time New Horizons arrived in July 2015, Pluto had been reclassified as a dwarf planet. The spacecraft travelled for 9½ years. 9½ years. Think about what you were doing 9½ years ago. How different was your life? Where were you living? What job did you have? What relationships were important to you? How has your world changed since then? That's how long New Horizons travelled. For most of that journey, the spacecraft was in hibernation mode. Its systems were powered down to save energy and reduce wear. It woke periodically for systems checks and trajectory corrections, then went back to sleep, like a patient traveller crossing an ocean, waiting to reach the distant shore. The spacecraft travelled more than 3 billion miles from Earth to Pluto, 3 billion miles, at that distance. Radio signals from New Horizons took about 4½ hours to reach Earth. That's a 9-hour round-trip communication time. If Mission Control sent a command, they'd wait 9 hours to find out if the command had been received and executed. On July 14th, 2015, New Horizons flew past Pluto at a distance of about 750 miles from the surface. The spacecraft was moving at about 31,000 miles per hour relative to Pluto, far too fast to slow down and orbit. New Horizons had one shot, one flyby, one chance to collect all its data. The spacecraft had been travelling for 9½ years for this single day. Actually, for just a few hours during that day when it was closest to Pluto, all the cameras, all the instruments, all the data collection happened in a brief window. Then Pluto was behind the spacecraft, receding into the distance. New Horizons couldn't turn around. It couldn't go back for another look. It was moving too fast, and it didn't have enough fuel to reverse course. One pass, that's all. But what a pass it was. The images New Horizons sent back showed a world far more complex and geologically active than anyone expected. Pluto's surface had mountains made of water ice, some as tall as the Rockies. On Earth, It had vast plains of nitrogen ice that appeared to be flowing and renewing themselves. It had a thin atmosphere that escaped into space, forming a tenuous tail, swept back by the solar wind. It had 5 known moons, the largest being Charon, which is so big relative to Pluto that some scientists consider them a binary dwarf planet system. New Horizons had revealed Pluto to be a fascinating, dynamic world. Not a dead, frozen rock at the edge of the solar system, but a place with active geology, complex surface features, and ongoing processes. After the Pluto flyby, New Horizons continued deeper into the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. In January 2019, nearly 13 years after launch, New Horizons flew past a Kuiper Belt object named Arakoth. Arakoth is a small, oddly shaped body about 22 miles long. It looks like 2 spheres stuck together. A contact binary formed when 2 separate objects merged gently in the early solar system. New Horizons' flyby of Arakoth was the most distant planetary encounter ever conducted. The spacecraft was over 4 billion miles from Earth. Light from that distance takes about 6 hours to reach us. And New Horizons is still going, it's still operational, still sending data, still exploring the outer reaches of the solar system. It will eventually leave the solar system entirely and enter interstellar space, joining the Voyager spacecraft as humanity's ambassadors to the cosmos. The journey to Pluto exemplifies the patience required for deep space. Exploration, 9 and 1/2 years to get there, one brief flyby, then years more travelling deeper into the Kuiper Belt. A mission lifetime that's already exceeded 18 years and will likely continue for years more, until the spacecraft's power supply finally runs out. Speaking of power, let's talk about how spacecraft survive these long journeys. For missions to the inner solar system, solar panels work fine. There's plenty of sunlight to generate electricity. Mars rovers use solar panels and they work reasonably well even on Mars, where sunlight is about 43% as strong as on Earth. But as you move farther from the sun, solar panels become less effective. At Jupiter, sunlight is only about 4% as strong as at Earth. At Saturn, it's about 1%. At Neptune, it's about 1/10 of 1%. Solar panels would be nearly useless. So spacecraft heading to the outer solar system use radioisotope thermoelectric generators, or RTGs. These are essentially nuclear batteries. They contain plutonium-238, which is radioactive. As the plutonium decays, it produces heat. Thermal couples convert this heat into electricity. RTGs are incredibly reliable. They have no moving parts, nothing to break or wear out except the slow radioactive decay of the plutonium itself. Plutonium-238 has a half-life of about 87.7 years. That means after 87.7 years, half of the plutonium will have decayed. The RTG will produce half as much heat and therefore half as much electricity. But for spacecraft missions lasting decades, this slow decline is predictable and manageable. Mission planners can calculate exactly how much power will be available at any point in the mission. Voyager 1 and Voyager 2 have been running on RTGs for nearly 50 years. Their power output has declined as the plutonium decays, but they're still producing enough electricity to run some of the spacecraft's instruments and transmit data back to Earth. Engineers have gradually shut down non-essential systems to conserve power. Heaters have been turned off, allowing some parts of the spacecraft to freeze. Instruments have been powered down one by one, but the core systems, the ones needed for communication and basic operations, are still running. The spacecraft are expected to have enough power to operate until sometime in the late 2020s. At that point, more than 50 years after launch, they'll finally go sing, but even then, they'll continue traveling through space, silent, dark, frozen, but intact, carrying their golden records as messages from humanity and music to any alien civilization that might Someday find them. The RTGs on Cassini powered the spacecraft for 20 years, from launch in 1997 to mission end in 2017. The RTGs on New Horizons are still powering the spacecraft 20 years after launch, and will likely continue for another decade or more. This technology is what makes long-duration outer solar system missions possible, but RTGs are expensive and politically complicated. Plutonium-238 is produced in nuclear reactors. The United States stopped producing it in the late 1980s. For years, NASA had to buy plutonium from Russia. Production restarted in the United States in 2013, but quantities are limited. There's not enough plutonium available to power every mission that might need it. This has become a bottleneck for outer solar system exploration. Mission planners have to carefully ration the available plutonium, deciding which missions are important enough to receive the precious fuel. Some proposed missions to the outer solar system have been cancelled or indefinitely delayed because there wasn't enough plutonium available. This is another challenge of exploring the solar system. Not just the travel time, but the limited resources. The scarcity of materials like plutonium, the competition for funding and launch opportunities, the need to prioritize some missions over others because we can't do everything. Now, let's talk about what might be possible in the future. Are we stuck with these long travel times forever? Or could we develop technology that would let us reach distant planets faster? The answer is complicated. The fundamental problem is energy. To go faster, you need more energy, and to carry more fuel to provide that energy, you need bigger rockets. Bigger rockets cost more money. At some point, the costs become prohibitive. Chemical rockets, the kind we use now, are fundamentally limited. They work by burning fuel and expelling the exhaust out the back. The speed of the exhaust determines how much thrust you get. Chemical rockets can only achieve exhaust speeds of a few miles per second. This limits how fast they can accelerate. A spacecraft, to go much faster, we'd need different propulsion systems. Nuclear thermal rockets are one possibility. Instead of chemical combustion, they'd use a nuclear reactor to heat propellant to extremely high temperatures. The superheated propellant would expand rapidly and be expelled out the back, creating thrust. Nuclear thermal rockets could potentially achieve exhaust speeds twice as high as chemical rockets. That would cut travel time significantly. A trip to Mars that takes 7 to 9 months. With chemical rockets, might take only 3-4 months. With a nuclear thermal rocket, a trip to Jupiter, that takes 5-6 years. Might take 2-3 years. Still long, but noticeably shorter. NASA and other space agencies have researched nuclear thermal rockets since the 1960s. Test reactors have been built and tested on the ground. The technology works, but no nuclear rocket has ever flown in space. The challenges are political and safety related, not technical. There's public concern about launching nuclear reactors into space. What if the rocket explodes during launch and spreads radioactive material? What if the reactor malfunctions in orbit? These concerns have prevented nuclear thermal rockets from being deployed, despite their potential benefits. Another possibility is ion drives. Ion drives work by using electricity to ionize atoms of propellant, usually xenon. The ions are then accelerated to very high speeds using electric fields and expelled out the back of the spacecraft. Ion drives produce very little thrust. You couldn't use an ion drive to launch a rocket from Earth's surface. The thrust is far too weak to overcome gravity. But in the vacuum of space, even tiny amounts of thrust can accumulate over time. An ion drive can run continuously for months or years, gradually accelerating the spacecraft to higher and higher speeds. The Dawn spacecraft, which visited the asteroids Vesta and Ceres, used ion drives. So did Deep Space One, a technology demonstration mission. Both were successful, but ion drives are slow to accelerate. They'd be useful for missions where you're not in a hurry and you want to minimize fuel mass. For human missions where time is critical, they're probably not the answer. Solar sails are another exotic option. A solar sail is a large, extremely thin, reflective sheet. Photons from the sun strike the sail and transfer momentum, pushing the spacecraft forward. The force is incredibly tiny. But in space, with no air resistance, even tiny forces can eventually accelerate a spacecraft to significant speeds. The advantage of a solar sail is that it needs no fuel. The sun provides the energy. The disadvantage is that the acceleration is very slow and it only works well near the sun where sunlight is strong. The LightSail 2 spacecraft launched in 2019 successfully demonstrated solar sail technology in Earth orbit. The Planetary Society's project showed that solar sails work, but using them for interplanetary missions would require very large sails and a lot of patience, even more patience than current missions. For truly fast interplanetary travel, we'd need something more radical, nuclear pulse propulsion, where small nuclear explosions are detonated behind the spacecraft to push it forward. This concept, called Project Orion, was studied in the 1950s and 60s. Theoretical calculations suggested it could achieve very high speeds, but the political and environmental challenges of setting off nuclear explosions in space prevented any real development fusion rockets, if we could ever get fusion power to work reliably, might offer very high exhaust speeds and tremendous thrust. But practical fusion power has been just 20 years away for the last 70 years. We're still not there. Antimatter rockets could theoretically achieve exhaust speeds approaching the speed of light, but producing and storing antimatter is incredibly difficult and expensive. We can create tiny amounts of antimatter in particle accelerators, but nowhere near enough to fuel a rocket, and storing it without letting it touch. Normal matter and annihilate would be a monumental challenge. The reality is that for the foreseeable future, we're probably stuck with something close to current travel times. Maybe nuclear thermal rockets could cut travel times by a factor of 2. That would be significant. 3 to 4 months to Mars instead of 7 to 9, 2 to 3 years to Jupiter instead of 5 to 6. But we're not looking at orders of magnitude improvement. We're not going to suddenly travel to Mars in days or to Jupiter in weeks. The physics won't allow it, and the engineering challenges are immense. This means that exploring the outer solar system will continue to require patience, decades of commitment to single missions, institutional support that outlasts political administrations and funding cycles, people willing to dedicate careers to projects that won't produce results for years. But here's the interesting thing. We've proven we can do this. We've sent successful missions to every planet. We've operated spacecraft for decades. We've maintained the institutional knowledge and commitment needed to see these missions through. The question isn't whether we can do it. We've demonstrated that we can. The question is whether we will continue to do it. Will we continue funding missions that take years to produce results? Will we maintain the scientific institutions that support long-term research? Will we educate the next generation of scientists and engineers to carry on this work? These are social and political questions, not technical ones. The planets aren't going anywhere. They'll be there whether we send missions to explore them or not. The question is whether humanity will remain curious enough, patient enough, and committed enough to keep exploring. Let's also consider what these travel times mean for the search for life. One of the most exciting possibilities in planetary science is that life might exist elsewhere in our solar system. Not intelligent life, probably, but microbial life. Simple organisms that could survive in extreme environments. Mars is the obvious candidate. Mars had liquid water on its surface billions of years ago. Rivers flowed, lakes existed, maybe even an ocean covered part of the northern hemisphere. Water is essential for life as we know it. Where there was water, there might have been life. And if life arose on early Mars, some of it might still survive today underground, protected from the harsh surface conditions in subsurface aquifers or hydrothermal system. Finding life on Mars would be one of the most profound discoveries in human history. It would prove that life isn't unique to Earth, that it can arise independently on different worlds, that the universe might be full of life in places we haven't looked yet. But searching for life on Mars is slow. Each rover mission takes 7 to 9 months to reach Mars. Then the rover operates for months or years, slowly driving across the surface, analysing rocks and soil, searching for biosignatures. Perseverance is currently collecting samples that will eventually be returned to Earth by a future mission, but that sample return mission won't launch until the late 2020s. It will take 7 to 9 months to reach Mars. It will collect the samples Perseverance has cached. Then it will launch from Mars and take another 7 to 9 months to return to Earth. Best case scenario, we won't have Mars samples in laboratories on Earth until the early 2030s, more than a decade from now, and that's if everything goes according to plan, which it rarely does in space exploration. The search for life on Mars is a slow, methodical process. Each mission builds on the previous one. Each discovery raises new questions that the next mission will attempt to answer. We're making progress, but it's measured in decades, not years. Other candidates for life include Europa, one of Jupiter's moons. Europa has a thick ice shell covering a subsurface ocean. The ocean is kept liquid by tidal heating from Jupiter's gravity. Where there's liquid water, there might be life, but Europa is far away, 5 to 6 years to reach Jupiter. Then you need to orbit Jupiter and study Europa specifically. NASA's Europa Clipper mission launched in October 2024. It will take about 5.5 years to reach Jupiter, arriving in April 2030. Europa Clipper won't land on Europa. It will orbit Jupiter and make repeated close flybys of Europa, using instruments to study the moon's ice shell and subsurface ocean. The mission will look for evidence of organic compounds, search for places where subsurface water might be reaching the surface, and try to determine if Europa's ocean could support life. But we won't get definitive answers about life on Europa from this mission. Europa Clipper is a reconnaissance mission. It will tell us where to look, what to look for, and how to design future missions. Actually, landing on Europa, drilling through the ice, and sampling the subsurface ocean would require a much more complex mission. That mission hasn't been designed yet, let alone built or launched. It could be decades before we have the technology and funding to send a lander to Europa. And then there's Enceladus, one of Saturn's moons. Enceladus has geysers that erupt from cracks in its south polar region. These geysers spray water, ice, and organic compounds into space. The material comes from a subsurface ocean similar to Europa's. Cassini flew through these plumes and analysed their composition. The plumes contain water, organic molecules, and energy sources that could support life. Enceladus might have everything necessary for life, but it's 7 years away. No mission to Enceladus is currently funded or even in development. It could be 20 or 30 years before we send a dedicated mission to study Enceladus and search for life in its subsurface ocean. This is the frustration of astrobiology in our solar system. The most promising places to search for life are far away. Reaching them takes years. Studying them takes years more. Building and funding the missions takes years before that, from initial concept to final results. A mission to search for life on Europa or Enceladus could easily span 30 to 40 years. An entire career, a significant fraction of a human lifetime. But this is what the search music for life requires: patience, persistence, commitment across generations, the willingness to pursue questions whose answers might not come for decades. Now, let's return to something we touched on earlier: the psychological challenge of long-duration space travel. For robotic missions, time doesn't matter. The spacecraft doesn't care if the journey takes months or years. It doesn't get bored or lonely. It doesn't miss home. But for human missions, psychology is one of the biggest challenges. Astronauts on the International Space Station typically stay for 6 months. Some have stayed for a year. Russian cosmonaut Valery Polyakov stayed for 14 months, the longest continuous space flight. These long-duration missions have taught us a lot about the psychological effects of space flight. Isolation is hard. Being confined to a small space with the same few people for months is stressful. You can't go outside, you can't get away. If you have a conflict with a crewmate, you can't avoid them. Astronauts are carefully selected for psychological stability. They undergo extensive training in teamwork and conflict resolution. They have regular communications with psychologists on the ground. And still it's difficult. Astronauts report feeling isolated, even though they're in constant communication with Earth. They miss their families. They miss fresh air, natural environments, the feeling of wind and rain. They miss privacy and personal space. Some astronauts adapt well and feel they could stay in space for much longer. Others count the days until they can return home. Now, imagine a mission to Mars, 7 to 9 months of travel in a spacecraft much smaller than the International Space Station. No possibility of resupply or evacuation. If someone has a medical emergency, crew has to handle it. If someone has a psychological crisis, the crew has to support them. No outside help is coming. Then you arrive at Mars and spend a year and a half on the surface conducting research and waiting for Earth and Mars to align for the return journey. Then another 7 to 9 months traveling back to Earth. Total mission time around 2.5 to 3 years, 3 years away from Earth. That's twice as long as anyone has ever stayed in space. And that's for Mars, the relatively easy destination. For Jupiter, you're looking at 5 to 6 years of travel each way, over a decade for a round trip. For Saturn, 15 to 20 years total. These timescales exceed anything humans have attempted. We simply don't know if people can maintain their psychological health for that long in the confined, isolated environment of a spacecraft. Maybe they can, maybe with careful crew selection, good training, and robust psychological support systems, humans could handle decade-long missions. Or maybe there are fundamental limits to how long people can stay psychologically healthy in isolation. Maybe after a certain point, the stress becomes too great, the monotony too oppressive, the isolation too complete. We won't know until we try, and trying means committing people to missions they might not survive, at least not with their mental health intact. This is one of the ethical challenges of deep space exploration. Is it right to send people on missions that might psychologically damage them, even if they volunteer, even if they understand the risks? These are difficult questions without easy answers. For now, robotic exploration avoids these problems entirely. Robots don't have psychological needs. They can travel for years without suffering. They can work in isolation without stress. They are the perfect explorers for distant worlds. But robots can't make the kinds of observations and decisions that humans can. A geologist on Mars could accomplish in an hour what a rover takes weeks to do. A human could recognize interesting formations, make intuitive leaps, adapt to unexpected discoveries in the ways that robots can't. There's a reason we still send human explorers to difficult places on Earth. Even though we have drones and remote sensing, human judgment, flexibility, and creativity are invaluable. The same would be true on other planets, so we face a trade-off. Robots are patient music and don't suffer, but they're limited in what they can accomplish. Humans are capable and adaptable, but they can't endure the journey to distant worlds, at least not with current technology. Perhaps future technology will change this equation. Maybe we'll develop suspended animation or cryogenic sleep that would allow humans to sleep through the journey. They'd be placed in hibernation shortly after launch and awakened when they arrived at their destination. The subjective experience of the trip would be brief, even if the objective time was years. This technology appears in science fiction constantly, but it's purely speculative. We have no idea how to safely put humans into suspended animation for years. We don't know how to prevent tissue damage from ice crystals during freezing. We don't know how to maintain basic bodily functions during extended hibernation. We don't know how to wake people up safely after years of sleep. Some animals can hibernate for months, but they don't go into true stasis. Their metabolism slows, but it doesn't stop. They still need some food reserves to burn during hibernation. Scaling that up to years of human hibernation is an enormous challenge. Maybe it will be solved someday. Maybe decades or centuries from now, we'll have the medical technology to put people to sleep for interplanetary journeys, but we don't have it now, and we're not close to having it. For the foreseeable future, humans who travel to distant planets will have to be awake for the journey, experiencing every long month of travel through the void, dealing with the psychological challenges as they come. This is yet another reason why the travel times matter so much. It's not just about the time it takes to get there, it's about what that time does to the people making the journey. Let's talk about one more aspect of these long missions: cost. Space missions are expensive, incredibly expensive, and the longer a mission takes, the more it costs, not just because the spacecraft has to be built to last longer, though that's part of it, but because you have to pay people to operate the mission. Every day a mission is active, there's a team of engineers, scientists, and support staff monitoring it, analysing data, planning operations, and solving problems. For a mission to Mars that lasts 7 to 9 months, you need a team for those 7 to 9 months, plus the time before and after for planning and data analysis. For a mission to Saturn that lasts 7 years, you need a team for 7 years. That's 7 years of salaries, benefits, office space, computers, and all the other overhead costs of keeping a team employed. The Cassini mission, from development through end of operations, cost about $1 billion. That's over 20 years. From initial development to mission end, $3.26 billion divided over 20 years is about $63 million per year. That's a lot of money. But actually, for what Cassini accomplished, it's remarkably cost-effective. Cassini returned hundreds of thousands of images. It made discoveries about Saturn, its rings, and its moons that filled textbooks. It fundamentally changed our understanding of the outer solar system. If you calculate the cost per discovery, or cost per unit of knowledge gained, Cassini was a bargain. But not every mission succeeds, and failed missions cost money too. Every mission that crashes before completing its objectives represents not just lost science, but lost investment. This is why mission success is so critical. It's not just about the science, it's about justifying the expense, proving to funding agencies and taxpayers, music, that space exploration is worth the cost. Every successful mission like Cassini or Voyager or Perseverance makes it easier to get funding for the next mission. Every failure makes it harder. This creates pressure on mission planners to be conservative, to choose mission designs that are likely to succeed rather than innovative designs that might accomplish more, but have higher risk. It's a natural human response to the high costs and long timescales involved. If you're spending billions of dollars and decades of effort, you want to maximize your chances of success, but conservatism can also limit what we accomplish in some of the most exciting mission concepts. Things like sample return from Mars or landing on Europa, or drilling into Enceladus's ocean, are risky and expensive. They push the boundaries of what's technically possible, They might fail, and if they fail, the cost is enormous. So they often get delayed or cancelled in favour of safer, cheaper missions. This is the paradox of space exploration funding. We want ambitious missions that make groundbreaking discoveries, but we're risk-averse because of the high costs and long timescales. The result is that really ambitious missions take a very long time to get approved and funded. A Mars sample return mission has been discussed for decades. It's finally being developed now with a planned launch in the late 2020s. From initial concept to execution, it will have taken 30 or 40 years. A human mission to Mars has been discussed since the 60s. We're still not close to actually doing it. Missions to the outer solar system face even longer development times because they're even more expensive and risky. This is why space exploration progresses slowly, not because we lack the technology, though technology is certainly a limiting factor, but because we lack the sustained commitment and funding to pursue ambitious long-term projects. Space agencies have to compete for funding with other priorities: healthcare, education, infrastructure, defense, snorts. All of these are important and all of them need money. Space exploration is wonderful, but it's hard to argue that it's more important than healthcare or education. So, space agencies work with limited budgets. They have to carefully choose which missions to pursue. They have to balance ambitious science goals with realistic costs and timelines. They have to prove that every mission is worth the investment. And when you're talking about missions that take years or decades to complete, proving worth becomes challenging. The people who approve funding might not be around to see the results. Politicians working on election cycles measured in years have trouble committing to missions measured in decades. This is a fundamental challenge for space exploration. The timescales don't match human institutions. We've built a society that thinks in terms of quarterly earnings, annual budgets, and multi-year election cycles. Space exploration thinks in terms of decades and generations. Bridging this gap requires vision and commitment that's rare in any human endeavour, and yet we've managed it. NASA has been operating continuously for over 6 years, the European Space Agency for over 48 years. Other space agencies around the world have maintained programs for decades. These institutions have persisted through changes in leadership, shifts in political priorities, budget cuts and expansions, and all the other challenges that organizations face. They've kept exploring, kept sending missions to distant worlds, kept expanding our knowledge of the solar system. This persistence to music is itself an achievement, maybe one of humanity's greatest achievements. We've created institutions capable of thinking and planning beyond the human lifespan, capable of committing to projects that will outlast any individual career, capable of maintaining knowledge and expertise across generations. This is how we explore space, not through individual heroics, though individual contributions are important, but through sustained institutional effort, through organizations that can plan missions in the 2000s that won't produce results until the 2030s or 2040s, through teams of people who understand they're building on the work of those who came before and laying groundwork for those who will come after, through a shared commitment to knowledge and discovery that transcends any single human life. So, when you think about the travel times to distant planets, remember that they're not just technical challenges, they're tests of human patience, commitment, and institutional resilience. Every mission that reaches its destination after years of travel is a victory, not just for science, but for human civilization's ability to think long-term. Every discovery made by spacecraft that traveled for years to reach their destinations is evidence that we can overcome our natural impatience and work toward goals that take decades to achieve. This might be the most important lesson from planetary exploration. Not what we've learned about Mars or Jupiter or Saturn, but what we've learned about ourselves, that we're capable of patience, that we can commit to goals that exceed individual lifetimes, that we can work together across decades to accomplish something remarkable. The planets aren't going anywhere. They'll orbit the sun for billions of years, whether we visit them or not. The question is whether we'll continue to have the vision, the commitment, and the patience to explore them. The travel times are what they are. Physics dictates how long it takes to reach distant worlds. We can't change that, at least not with current technology, but we can change how we think about these timescales. We can embrace the patience required. We can commit to missions that take decades. We can build institutions that persist across generations. We can educate young people to carry on this work when we're gone. This is how we explore the solar system, not by conquering space through brute force or speed, but by persisting, by being patient enough to wait years for our spacecraft to arrive, by being committed enough to support missions that won't produce results in our lifetimes, by being visionary enough to see value in knowledge that might not have immediate practical applications. The travel times to the planets are long, brutally long by human standards, but we've proven we can handle them. We've sent spacecraft to every planet. We're operating missions that have lasted for decades. We're planning future missions that will travel for years to reach their destinations. And every one of these missions, every image returned, every measurement made, every discovery announced, adds to our understanding of the universe we inhabit. That knowledge is worth the wait, worth the years of patient travel through the void, worth the decades of institutional commitment, worth the careers spent operating distant music spacecraft, because ultimately, this is who we are as a species. We're explorers. We look at distant lights in the sky and wonder what they are. We build machines to go there and find out. We wait years for those machines to arrive and send back their discoveries. And we marvel at what we learn. The travel times are long, but we have time, and we have patience, and we have an entire solar system music waiting to be explored. One patient mission at a time. But let's get even more specific about what music these journeys actually look like. Because the numbers are one thing, the human experience behind them is something else entirely. Consider the team operating the Curiosity rover on Mars right now. Curiosity landed on Mars in August 2012. It's been operating for over 13 years. That's over 13 years of daily operations. Every single day, a team of scientists and engineers works together to plan what Curiosity will do. They analyze the images and data from the previous day. They discuss what they saw, what it means, where the rover should go next. They debate which rocks to examine, which instruments to use, how to position the rover's arm and cameras. They write software commands that will tell the Curiosity exactly what to do. Then they send those commands to Mars. The commands travel at the speed of light, taking anywhere from 4 to 24 minutes to reach Mars, depending on where the planets are. Curiosity receives the commands, executes them autonomously, and sends back music the results. Those results take another 4 to 24 minutes to reach Earth. By the time the operations team sees what Curiosity did, it's already ancient history. The rover might have been finished with. The commanded activities for 15 or 20 minutes. This is called Mars time delay, and it shapes everything about how rovers are operated. You can't drive a Mars rover like a remote control car. The delay is too long. By the time you saw an obstacle and sent a command to stop, the rover would have already driven into it. Instead, rover operators work on Martian time. A Martian day, called a sol, is about 24 hours and 39 minutes long. 39 minutes longer than an Earth day. That doesn't sound like much. But it adds up. After a week, Martian time and Earth time are nearly 4½ hours out of sync. After a month, they're nearly a day off. Rover teams often work on Mars time, shifting their schedules every day to stay synchronized with the rover's day-night cycle. Today, you might start work at 9 Mercury, Tomorrow, you start at 9:40 a.m. The day after, 10:20 a.m. Your work schedule drifts later and later each day, music, until eventually you're working through the night. Then it drifts around back to morning. Again, this is incredibly disorienting for the human body. Your sleep schedule is constantly shifting. You're never fully adjusted. You're always jet-lagged. Some team members report having dreams about Mars, about being there on the surface, about seeing the landscapes through the rover's eyes. The line between their lives on Earth and their work on Mars blurs. They spend so much time thinking about Mars, planning for Mars, analysing data from Mars, that it becomes weirdly real to them. More real than the mesh and control room they're sitting in. This goes on for months. Some rover missions have maintained Mars time operations for 3 or 4 months continuously. It's exhausting, but it's necessary to maximise the rover's productivity. When you're operating a $2.5 billion on another planet, you want to get as much science done as possible, and that means working on Mars time, no matter how hard it is on the humans involved. Now, imagine scaling this up to a human mission. Astronauts on Mars would be living on Mars time naturally, but mission control on Earth would face the same challenges. Only now, instead of operating a rover, they'd be supporting human explorers. The stakes would be higher, the decisions more critical, the stress more intense, and it would go on not for months, but for the entire duration of the surface mission, probably a year and a half or more. The people supporting that mission would need to sustain this kind of effort for over a year, working irregular hours, living out of sync with Earth, maintaining constant vigilance in case something goes wrong. It's one thing to ask this of people for a few months. It's another to ask for a year or more. This is yet another hidden cost of the long travel times, not just the months spent travelling, but the months or years spent operating the mission after arrival, the sustained human effort required to make it all work. Let's talk about something else that rarely gets mentioned. The aging of spacecraft. When a spacecraft launches, every system is new, fresh from testing and verification, working perfectly, but space is harsh. Cosmic radiation bombards the spacecraft constantly, and high-energy particles strike the electronics, potentially causing failures. Temperature swings are extreme. In sunlight, surfaces can heat to hundreds of degrees. In shadow, or they can drop to hundreds of degrees below zero. This constant thermal cycling stresses materials. Metal expands and contracts. Seals and gaskets get brittle. Lubricants in moving parts can freeze or evaporate. Dust accumulates on solar panels, reducing their efficiency. Battery capacity decreases over time. Moving parts wear out, and there's no maintenance, no one to replace a worn bearing or fix a stuck mechanism. If something breaks, that's it. The spacecraft has to work around the failure or the mission ends. Engineers design spacecraft with redundancy to handle this. Critical systems have backups, sometimes multiple backups. The Voyager spacecraft have redundant computers, redundant transmitters, redundant attitude control systems. If one fails, the spacecraft can switch to the backup. But eventually backups run out. You can't plan for everything. Spirit. One of the Mars rovers that landed in 2004 got stuck in soft soil in 2009. Despite months of effort, engineers couldn't free it. Eventually, the rover's solar panels, stuck in an unfavorable position, couldn't generate enough power to keep it warm through the Martian winter. Spirit froze and never woke up. The mission ended not because the rover stopped working, but because it got physically stuck in a position where it couldn't survive. Opportunity. Spirit's twin rover operated for over 14 years until a global dust storm in 2018 covered its solar panels. The rover went to sleep waiting for the storm to clear and sunlight to reach its panels. but the storm was so intense, music, and lasted so long that Opportunity's batteries completely discharged. When the dust finally settled, the rover couldn't wake up. Engineers sent commands for months hoping Opportunity would respond. It never did. Most likely, the extreme cold during the storm damaged something critical or the batteries degraded beyond recovery. After 14 years of operation, Opportunity had finally run out of luck. These rovers lasted far longer than their planned 90-day missions. 14 years for Opportunity, 6 years for Spirit. But eventually, time caught up with them, and time catches up with everything. Cassini's mission ended when it ran low on fuel. After 13 years orbiting Saturn, making hundreds of orbits, flying past dozens of moons, the spacecraft was nearly out of propellant. Without propellant, Cassini couldn't control its orbit. It would eventually crash into one of Saturn's moons. To prevent contaminating potentially habitable moons like Enceladus with Earth microbes, NASA decided to deliberately crash Cassini into Saturn's atmosphere. On September 15th, 2017, Cassini made one final plunge into Saturn. As it descended, it transmitted data about Saturn's atmosphere until the increase in atmospheric pressure and heat music tore the spacecraft apart. The mission ended dramatically, but it ended by choice, a controlled conclusion rather than a slow decay into failure. This is how most planetary missions end. Either something critical breaks and the mission fails suddenly, or the spacecraft slowly runs out of resources, fuel, power, and the mission is deliberately concluded before random failure occurs. Very few spacecraft just keep working indefinitely. Time, radiation, and the harsh environment of space eventually take their toll. This means that mission planners have to think not just about how long it takes to reach a destination, but about how long the spacecraft can operate after it arrives. If it takes 6 years to reach Saturn, and you want to study Saturn for 4 years, you need a spacecraft that can function reliably for at least 10 years, preferably longer to provide margin for unexpected delays or problems. Cassini was designed for an 11-year mission. It actually operated for 20 years. That's remarkable engineering. But it's also rare. Most spacecraft don't last twice their design lifetime. This puts pressure on mission design. You want to build spacecraft that last as long as possible to maximize science return. But making spacecraft more robust and reliable adds weight, complexity, and cost. There's a trade-off. A simple, cheap spacecraft might only last its designed mission lifetime. A more expensive, robust spacecraft might last much longer and return far more data. Which is better depends on your goals, your budget, and your risk tolerance. NASA tends toward robust and expensive missions that are likely to succeed and operate for extended periods. This maximizes science return and justifies the high cost, but it also means fewer missions overall because each one is so expensive. Other space agencies and private companies sometimes choose cheaper, simpler missions that might have higher failure rates, but allow more missions to be attempted. Different philosophies, different approaches, no one right answer. But all of them have to grapple with the same fundamental problem: time. The time it takes to get music to distant destinations. The time spacecraft must operate to accomplish their goals. The time required to analyze the data they return. The time needed to plan, fund, build, and launch the next mission. Everything in space exploration is measured in time, and time is the one resource we can never get more of. Now, let's talk about one of the most impressive aspects of these long missions. The people who operate them often aren't the people who built them. Think about this. The New Horizons mission to Pluto launched in 2006. It reached Pluto in 2015, 9 and 1/2 years later. Some of the scientists who proposed the mission in the 1990s were retired by the time New Horizons arrived at Pluto. Some of the engineers who designed the spacecraft had moved on to other projects or other companies. But the mission continued. New people joined the team. Young scientists who were in high school when New Horizons launched became research scientists analysing the data from Pluto. Engineers who were undergraduates when the spacecraft was built became operations specialists commanding it in the Kuiper Belt. The mission spanned generations, not in the sense of parents and children, but in the sense of early career and late career scientists. People at different stages of life contributing to the same long-term project. This is unusual in most fields. Most projects don't last long enough to span careers like this. You start a project, you finish it, you move on. But planetary missions can last longer than entire careers. Someone might spend their entire professional life working on a single mission, from graduate student helping with early design work to postdoc during development and testing to research, scientist during the cruise phase to senior scientist during operations at the target planet, to Professor Emeritus analysing the final datasets. An entire career, 30 or 40 years connected to one mission. This creates a deep sense of ownership and commitment. These aren't just jobs to the people involved, they're life's work. Decades of effort poured into a single scientific endeavour. When Cassini ended its mission in 2017, some of the scientists and engineers who'd worked on it cried. They'd spent 20 years with this mission. Some had spent their entire adult lives working on Cassini. And now it was over. The spacecraft was gone, destroyed in Saturn's atmosphere. The mission they dedicated years to was complete. It was a success by any measure. Cassini had accomplished everything it set out to do and more, but it was still an ending, a loss, the end of something that had defined their professional lives. This emotional connection to missions is real and powerful. People form bonds with these spacecraft, not in a romantic sense, but in the sense of long-term partnerships. You work with something for years or decades and it becomes part of your life. You celebrate its successes. You stress over its problems. You mourn when it ends. The rovers on Mars have fan clubs. People around the world followed Opportunity's journey for 14 years. When the mission ended, when Opportunity stopped responding after the dust storm, people grieved, not just the mission team, but regular people who'd never worked for NASA. They'd followed the mission online, seen the images Opportunity sent back, read about its discoveries, and they felt connected to this robot explorer on another world. When it fell silent, they felt the loss. NASA received messages from people around the world expressing their sadness. Some were heartfelt tributes to Opportunity's accomplishments. Some were more light-hearted, joking that Opportunity had earned its rest after 14 years of work, but all of them reflected genuine emotion. People cared about this rover, this machine millions of miles away, because it represented something larger than itself. Curiosity, exploration, the human drive to understand our place in the universe. Opportunity wasn't just a robot, it was our representative on Mars, our eyes and hands on another world. And when it stopped working, part of our connection to Mars was lost until the next rover arrived and the cycle began again. This is the human side of space exploration that doesn't make it into the technical papers or the mission summaries. The emotional investment, the long-term commitment, the sense of purpose that comes from working toward goals that exceed individual timescales. The people who explore space through robotic proxies don't do it for the money. The salaries aren't spectacular. They could make more in private industry. They don't do it for fame. Most mission scientists and engineers work in obscurity. Their names aren't known to the public. They do it because it matters, because expanding human knowledge is worthwhile, because being part of something larger than yourself, something that will outlast you, gives life meaning. The long travel times to distant planets don't discourage these people. If anything, the patient commitment required attracts a certain type of person. People who can think long-term, who can delay gratification, who can work toward goals years in the future without needing immediate results. These are the people who make planetary exploration possible, not the astronauts. Though they are important when humans go to space, but the engineers, scientists, operations specialists, and support staff who design missions, build spacecraft and music, and operate them for years or decades. Without their patience and commitment, we'd know almost nothing about the other planets. Every image of Jupiter's storms, every measurement of Saturn's magnetic field, every rock sample analyzed on Mars exists because someone spent years working to make it happen. Years of their life invested in these missions. Years of patient dedication to exploration. This is worth recognizing and celebrating, not just the discoveries themselves, but the human effort behind them, the patience required to wait years for spacecraft to arrive, the persistence required to keep missions operating for decades, the commitment required to dedicate careers to single missions. These long travel times test us. They test our patience, our commitment, our ability to think beyond immediate results. But we've passed that test repeatedly. We've proven we can wait, we can commit, we can dedicate ourselves to goals that take decades to achieve, and that's worth celebrating, because it says something profound about human nature. We're not just creatures of immediate gratification. We're capable of patience, of working toward distant goals, of caring about things that won't benefit us directly. We can plant trees whose shade we'll never sit under. We can build cathedrals we'll never see completed. We can send spacecraft to distant worlds knowing the data won't arrive for years. This capacity for long-term thinking is one of humanity's greatest strengths. It's what allows us to address challenges like climate change that span generations. It's what allows us to build institutions that outlast individual lifetimes. And it's what allows us to explore the solar system despite the immense travel times involved. The planets are far away. Reaching them takes years, studying them takes years more. But we do it anyway, because the knowledge is worth the wait, because exploration is part of who we are. Because understanding our place in the universe matters. The travel times are what they are. We can't change the laws of physics. We can't make the distances shorter or the journeys faster, not with current technology. But we can change how we think about time. We can embrace patience as a virtue, other than seeing it as a burden. We can commit to long-term goals knowing we might not see the completion. We can work towards discoveries that will benefit future generations rather than ourselves. This is the mindset that makes space exploration possible, and it's a mindset worth cultivating in other areas of life as well. Because most worthwhile things take time. Learning a skill takes years of practice. Building a career takes decades of work. Raising children takes 2 decades of patience and commitment. Creating lasting change in society takes generations. We live in an era of instant gratification where we expect everything to be fast and easy. But the most valuable things in life aren't fast or easy, and they require time, effort, and patience. Space exploration teaches us this lesson in the most dramatic way possible. You can't rush a mission to Saturn. The journey takes 7 years. No matter how impatient you are, you have to wait. And in waiting, you learn patience. You learn to find satisfaction in the journey itself, not just the destination. You learn to appreciate incremental progress, each milestone reached, each course correction executed successfully, each system check passed. These small victories accumulate over years into major achievements. This is true not just in space exploration, but in life generally. Major accomplishments are built from small daily efforts sustained over long periods. The travel times to the planets remind us of this truth. They force us to be patient, to think long-term, to value persistence and commitment, And in doing so, they make us better, not just as explorers, but as human beings. So when you think about how long it takes to reach other planets, remember, these aren't just numbers, they're tests of human character, challenges that push us to be more patient, more committed, more capable of long-term thinking. And every mission that succeeds after years of travel is evidence that we can pass these tests, that we can be patient when patience is required, that we can commit to goals that exceed our lifetimes, that we can work together across decades to accomplish extraordinary things. The solar system is vast, the journeys are long, but we're making them. One patient mission at a time, and in doing so, we're not just exploring space, we're discovering what we're capable of as a species, our capacity for patience, our ability to commit, our willingness to pursue knowledge for its own sake, even when the pursuit takes years or decades. This is who we are at our best, and the long journeys to distant worlds bring out that best in us.